Okay, this video is about diagnostic tests for regression and what happens when things go wrong. Before we get into all of that, I want to redefine what it means to be normally distributed. Let's suppose we have a random variable x that is normally distributed like this. Then I could also write the same thing like this. That x is equal to the mean plus a random error. The mean of the error term is 0, so there's an equal chance that it could be positive or negative, or in this case, above or below average. And the variance of the error term is the same as the variance in the first distribution, so both of these expressions are exactly the same thing. And this is going to apply in the next part when I talk about regression assumptions. Every hypothesis test we have done this term had some assumptions behind it. For example, the two-sample t-test assumes that the populations are independent and normally distributed. I didn't make a fuss about it at the time, since our data sets rarely, if ever, challenged these basic assumptions, but they were always there, lurking in the background. And if any assumption gets violated, then the whole theory behind the test is compromised. It's like a castle built on sand. If the foundation is weak, then the whole thing will fall over. This is becoming more important because as our hypotheses become more advanced, they also tend to become with more and more assumptions. A regression has 4 assumptions behind it. The first is the model form. We assume that the true relationship between x and y is linear. Furthermore, the random observations or data points miss this line by a random error. The other 3 assumptions are about this random error term. Next, we assume that the errors are independent. And we also assume that they are normally distributed with a mean of 0. And finally, we assume that the variance of the error term is constant. We call it sigma squared. The error term should remind you of the alternative definition of the normal distribution from the previous slide. And there's a nice way to summarize the 4 assumptions by combining them into the usual definition of normal. If we are given an x value, then the y value is independent and normally distributed. And the center of the distribution is a point on the true line relating x and y. We would plug in the x value into this line equation to find the mean of the distribution. And then it has a variance of sigma squared. So all 4 assumptions can be simplified into one statement about a normal distribution. And the MSE from the ANOVA table is still our best estimate of sigma squared. If any of these 4 assumptions seem to be violated, then we have a real problem on our hands. It makes our statistical theory questionable, and we might not even be able to trust our ANOVA F statistic or T statistic. So any good regression should test the assumptions before going too far. I'm going to show you ways to check all 4 of the assumptions. All of these diagnostic tests are done by making a graph or chart and then using your best judgment. We're going to use the pizza sales data again as our example. And we'll start with the one graph that every regression should include, the residual plot. This graph tests 2 assumptions, the model form and constant variance. In order to make the graph, we first need to calculate the residual for every point. Our best fit line equation is y equals 5x plus 60. So let's plug in all of our x values, to get these y hat values. Next, to find the residuals, we subtract y hat from y. And now we can make the residual plot. We place residual on the y-axis and y hat on the x-axis and plot each point. For example, our first data point has a y hat value of 70 and a residual of minus 12, so it is plotted here in the residual plot. And this graph is a good example of what we hope to see. We want a nice random cloud of points around the x-axis. If we see a trend or any other clear shape in the data, then it would be a problem. And later on, we'll see some examples of that. Next, we can test the assumption that errors are normally distributed by making a histogram of the residuals. We already calculated the residuals in the last slide, so I'll just make a histogram of them. What we would like to see is a normal bell-shaped distribution centered at 0. Some of you might look at this and see a problem, but you have to consider that our sample size is only 10. Any histogram with only 10 observations probably isn't going to look like anything. And to be honest, I've noticed that most freshmen look at histograms expecting them to be perfect and then get upset when they aren't. Histograms are very rough estimates of the shape of a distribution, and you have to give them the benefit of the doubt. When I look at this histogram, I think about it like this. It isn't very non-normal, so it's fine. You can't really expect your histograms to look much like a normal distribution. You should just watch out for histograms that are obviously not normal. Those are the problems. And if you do happen to have a very non-normal histogram, then it doesn't have to be the end of the world. The central limit theorem can be your friend. A large enough sample size makes everything normal in the end. So even if you have a very non-normal histogram, if your sample size is quite large, then you won't have a problem with your analysis. Finally, I'm going to show how to check the assumption of independence. This assumption is rarely tested because there is rarely any reason to question it. For example, why would we suspect that the residual pizza sales in our town depends on the residual pizza sales from some other town? That would be some really paranoid thinking. But let's see how it all works anyways. We're going to plot our residuals again, but this time we're going to plot them versus observation number. You can see over on the left, I've labeled the pizza restaurants from 1 to 10, or data point number 1 to data point number 10. And we place that on the x-axis. Finally, we typically connect the points with straight lines to make it easier to follow from left to right. This graph is a good example of what we hope to see. The graph should randomly bounce up and down, sometimes large jumps, sometimes small jumps. There is no clear pattern to be seen, and that indicates independence. All right, now that I've shown you all the diagnostic tests for the 4 assumptions, let's start looking at examples where all goes wrong. We'll begin with an example that violates the model assumption. This is a scatter plot of sales versus experience for 15 workers. Just by looking at the plot, you can already begin to tell that it doesn't follow a straight line trend. Let's add the best fit line of the graph. If anything, it just makes it even clearer that the data points do not follow a straight line. Let's calculate the residuals and make the residual plot. Here's the residual plot. The curved pattern is even more exaggerated in this plot. And remember, we hope to see a random cloud of points with no trend or pattern. There's a pretty clear trend in this plot, so we'd have a good reason to believe that the relationship between x and y is not linear. And we'll talk more about nonlinear relationships in a couple weeks. And next, we'll look at a scatter plot with non-constant variance. In this example, the x variable is car weight, and the y variable is fuel efficiency, measured in miles per gallon. Let's add the best fit line. There is a pretty clearly nothing wrong with the model form. Fuel efficiency decreases linearly as car weight increases. But let's calculate the residuals and plot them. Here's the residual plot. The problem with this graph is that the width of the cloud keeps changing, and this indicates non-constant variance. Our random cloud of points should have more or less constant width. Throughout the whole thing. This particular plot has what we call a fan shape. The width starts very small, but then increases as we move to the right. The fan shape is probably the most common way to see non-constant variance, but it isn't the only way. Any residual plot with non-constant width has the problem of non-constant variance. If your data has non-constant variance, then there is very little you can do about it. There are a couple of last resort tricks you can try, and I'll talk about them in later videos. Now, non-constant variance by itself isn't the worst thing in the world. Looking at this data, I would still trust the results of the hypothesis test if it said that there was a significant linear relationship between car weight and fuel efficiency. The big issue with non-constant variance is trying to make prediction intervals. There is absolutely no way to estimate fuel efficiency for all the different cars using the MSE as the one and only variance estimate. Clearly, these cars on the left have smaller variance, and these cars on the right have larger variance. There is no way to do a one-size-fits-all prediction interval that works throughout the whole data set. Next, we have an example that I just made up to demonstrate a really non-normal distribution. Here's a scatter plot with the best fit line added in. Pause the video for a minute and look at this graph. See if you can deduce what the residual histogram is going to look like. Okay, if you had your guess, does it look like this? This is the residual histogram for this data set. It has two distinct peaks called a bimodal distribution and is very much not normal. Hopefully you were able to predict this shape. There are very few, if any, data points near the best fit line. They tend to clump together some distance away from the line. Specifically, there seems to be a distinct clump above the line and a distinct clump below the line. Even though this data is artificial, it isn't hard to imagine a situation that would result in a scatter plot like this. Imagine a company where everyone was either a manager or a worker. And suppose we collect a random sample of employees and plot salary versus experience. Both managers and workers would get higher salaries if they have more experience. But then obviously managers also make much larger salaries than workers. So our sample of data points would be split into two distinct groups, the managers and the workers. If you got a data set like this in real life, then the sensible thing would be to separate the manager's data from the worker's data and just analyze them separately. All right, next we'll look at a data set that doesn't have independence. This data set is called a time series because it is collected at regular time intervals. Specifically, we have one data point every year at Christmas for 20 years. Time series are a type of data where independence is a real worry. It is entirely possible that the residual from year 1 could affect the residual of year 2, and so on. Anyway, let's look at the data. Our x variable is snowfall, and the y variable is ski lift ticket sales. We also see a somewhat positive trend confirmed by the best fit line. This seems reasonable to me. More snowfall means better ski conditions. Anyway, let's look at the residual plots. First, the regular residual plot of residual versus y hat shows nothing wrong. There's no problem with the assumptions of the model form or constant variance. There is, however, a problem with the assumption of independence. When we plot the residuals versus year, we see a very clear pattern. Remember that we hope to see a random-looking plot of big and small jumps with no discernible pattern. This graph pretty clearly shows a rising overall trend of the residuals over time. So the error terms are not independent for this data set. This is quite easy to fix, but we'll have to wait until the next round of videos to see how. Before going on, we needed to learn more about lack of independence. When a time series exhibits non-independence like the last video, then it is called autocorrelation. And there are two kinds of autocorrelation, positive and negative. You need to be aware of both kinds and watch out for them. Positive autocorrelation is what we saw in the last example. There are mostly small jumps that add up over time to create an overall trend. Negative autocorrelation, on the other hand, has a graph that constantly swings back and forth. The jumps are mostly very large and usually go back in the direction of where it came from. Those are the characteristics of autocorrelation. Ideally, your residual plot will show neither of these extreme behaviors. There are just a few other dangers and incorrect uses of regression that I need to point out. Most of them can be avoided by graphing the data points and using a little common sense. The first thing to point out is that sample correlation can only detect linear trends. It is absolutely useless with curved or nonlinear trends. For example, here is a data set that is a perfect parabola. What do you think the correlation of this data set is? That's right, exactly 0. From the perspective of the sample correlation calculation, this data set may as well be a random cloud of points. The lesson is that you should always make scatter plots of your data. Correlation is a useful tool, but it can't tell the whole story by itself. Your eye can help you make sensible choices, even if the computer seems to disagree. The next thing to mention is outliers, or sometimes they are called influential points. These are points that are located very far away from the group. For example, here is a data set with one point far removed from the others. And the best fit line for this data set is also shown in the graph. Next, I'm going to remove that outlying point and show how much of an effect it has. After deleting the point, the slope of the best fit line is more than 2 times larger. That's a substantial difference. If we had, for example, deleted one of the points in the group instead of the outlier, then the line would barely move. Remember that the best fit line has to minimize the squared distances between the points and the line. 1 point more or less in this bunch isn't going to have much effect. But 1 point way out by itself can literally drag the line to it. And that is the danger of outliers. Their abnormal distance from the group gives them an incredibly strong effect on the best fit line. When you see outliers in real life, the first thing you should do is double check the data. To err is human, and to be perfectly honest, we do not have our best and brightest people working in data entry. So mistakes will happen. If you double check the data and determine that it is not a mistake, then you just have a really unusual point in your data set. Finally, I want to talk about extrapolation. This means using your best fit line to make predictions well outside of your data set. In our pizza sales example, all of our towns in our data set had between 2,000 and 26,000 students. And I would feel very comfortable making predictions about pizza sales within that range. But as we get farther away from that range, then predictions are much harder to justify. For example, we could estimate pizza sales at Ohio State University with over 60,000 students by extending our best fit line out to where x is equal to 60. But this is so far away from our data set, and we have absolutely no proof that this linear trend goes on forever. It's entirely possible that pizza sales increase for a while and then flatten out and level off after a certain point. Or it is equally possible that pizza sales grow exponentially with student population and grow even faster. All of these various possibilities would look like linear trends in this window where our data points lie. But we have no guarantees for what happens next. There's nothing mathematically wrong with extrapolating this line to make predictions. But common sense tells us that we need to be careful about it because we are making a pretty big assumption. Finally, here is a made-up data set with an outlier. The complete data is shown over on the left, and other useful information is shown on the right. You should copy this down since you'll need it to answer the 3 questions coming up. Good luck with that, and I'll see you in class.